Alright, so good to go. Alright, so we looked at the different types of analyses that we'll be considering. I introduced a set of different types of problems that we'd encounter, and so from that set, today we're going to deal with the first type of problems, which is linear systems. Now, it's really a group of procedures. The first linear system is the first in a set of procedures, and the other procedures would be root finding or solving a nonlinear equation, and the other one is optimization. Alright, so we're going to go through linear systems today, and then our next class, which will be next week, is going to be root finding, and the week after that, or the next time we meet, we'll be doing optimization. So let's deal with root finding. Alright, so today what we're going to do is we're going to look at what's a linear system. We're going to identify simple methods for solving linear systems. Some of these things you may know already. So the goal of this is not going to be to learn the simplistic view of linear solving, but more applications. Alright? But we will still go over the basics. There's going to be a lot of information on the basics, but it's not that way. I don't intend to spend too much time going over the basics, because we don't want to bog down ourselves in the simple use of it, or the mathematical use of it, and miss the engineering application. So we want to get to the engineering application quickly. Alright, so let's just get to it. Alright, so here we have a problem. It's a normal problem. What you have there is called A11 times x1 plus A12 times x2 equal b. Now that's a very mathematical statement. It's a little abstract. Doesn't even make much sense. But what it's really saying is that you have two, what we call, variables. In engineering, we rather say something like quantities or properties or physical systems or something like that. And these two physical systems, that's x1 and x2, they are related by this expression. That means x1, which is a physical parameter, or one physical parameter, scaled by A11, and if you add that parameter to another physical parameter of your system, it results in this thing called b, just a constant. That means regardless of what x1, parameter x1 and x2 are, it doesn't change what b is. So it's this relationship. Okay? This is called a proportional relationship. Proportional meaning when you double one, the effect sort of doubles. When you half one, the effect sort of halves, based on the type of quantity that you're looking at. Alright? So we call this a linear relationship. Linear relationships are very common in engineering. And now, oftentimes, so as I said, the quantity, we call it a variable in math, and we call it a linear equation. Now, an equation like this, how many quantities are in this equation, as described here? How many things vary? How many things are we looking at how they relate to each other? Two. The two things are called here x1 and x2. As I said, sometimes it takes a little time to take the journey from math into engineering. So we have to try, and that's what this one of the purpose of this course is, to get the root math that we are used to out of our minds and start seeing it in a more real world sense. So here we have two variables, two things that can change, and we're looking at how they relate. But so this one equation has two. This is the simplest type of linear equation. It must have at least two variables. Okay? If an equation doesn't have two variables, it's not an equation. It's a constant. X equals something. That's a constant. Alright? Or it's not a relationship. So it's a plain constant. So the simplest linear system must involve two variables, or we say two quantities. You can have a more complex linear system, and that is, in that case, we have several we can have several relationships. Yes. They're not hearing either? And I'm hearing them.
Can anyone hear? Can anyone hear me?
Can anyone hear?
Yes, I'm here. No.
You're hearing?
I'm hearing me, and I'm not hearing the teacher.
Let's see what's going on. Hold on a minute.
I think the teacher's internet is shaky, because I'm not hearing him.
Bear with me.
Hello?
Folks.
Yeah, I'm the Derek. I'm not the teacher. Putting that out there.
Hearing me now, right?
Okay.
Yes, wait.
Alright, mute your mic. Let me share screen. Alright, and you're seeing the I hope you're seeing the PDF now, the PowerPoint now.
Loaded.
Seeing it now? Give me a minute, people.
It's loaded.
It's loading, okay. As soon as it's loaded, let me know. Jayan, you're seeing the PowerPoint? Type your answer for me.
No, I'm not seeing anything.
Not seeing anything.
Yeah.
Alright, I'm doing another option. Everybody's hearing me now though, right?
Yeah.
Alright, so what I'm going to do, I'll actually send you the PowerPoint presentation. It will actually just come across to you through Skype. So you just download it, I'll tell you where I am, and you follow along. Alright? So you'll soon see it. Confirm that you're seeing it, okay? Jay, and you say yes. Yes to what?
Oh, you asked if I was hearing, so yes, I'm hearing.
Okay, alright.
Yeah.
I don't think this will recur, but we have to iron it out, right? So let's bear with me. So I am at this slide here. Everybody's seeing the slides, right? Alright, good. Alright, we're good to go. So a linear equation can have several quantities that are related to each other, more than two. The simplest, of course, is two, but you can have several. And a linear system are several relationships. Alright? So you can have several things related to each other by different laws. So since I deal with energy a lot, let's talk about energy. Doesn't really concern some of you, but let's say you have a linear equation that relates temperature and pressure, some law, physical law, like ideal gas law, based on the system you're looking at. Then you have another equation, a different physical law or phenomena that also relates temperature and pressure. Not the ideal gas law, but it's also true. Let's say it applies to mechanics. And then there may be another relationship that may not apply to mechanics. It may have to do with electrical properties or something. And then there's another equation, and this could go on. But they all still involve pressure and temperature. Alright? So all of those together, a system has to have what's called a solution. There must be somewhere in which all those equations are true. And wherever they are all true is the solution to the system. Okay? So it's a value for the temperature and pressure and whatever other properties may exist. A value for which in all the laws that temperature and pressure are applicable, the hold or the solution or the equations which would have expressed these laws would have been valid for those quantities, for all of them. Alright? That's called the solution to the system. Okay? Now in math, we have several ways in which the system might be applied. This is an example. This is a mechanics problem. Not going to solve it here, but you'll do a little exercise in it for an assignment. So this is a problem involving some springs and a mass and some masses, and each mass is subjected, or in each condition for each mass, Newton's first law of motion must be valid. That means, assuming the system is not moving, each mass is at a certain location, all the springs are stretching. They are stretching based on Hooke's law, we call it. That's one law by itself. But then there's also Newton's first law. That's another law by itself. And then there are several masses. So each system, okay, must obey Newton's law and each system must obey Hooke's law. But all the systems are physically in contact with each other. So because they're all physically in contact with each other, then the variable, which is x, that is what we want to know. Where are the masses at rest? That's the question. That means if I was to displace it and let it go, where would it come to rest? That would be the solution, right? Because we call it equilibrium in mechanics, the place where things stop moving. So this is an example of, in this case, it would have to be 1, 2, 3, 4, 5, 6 masses. So this is 6 masses. There should be 6 laws of mechanics, 6 Newton's first laws of each mass. So that would be 6 equations there. You also have several springs. These 4 actually make one spring. They are just divided. K3, K3. No, these 2. I have 2 more here. There's 1 there. But there are all these several springs. Each spring itself is also obeying its own law. And so you have all these expressions. And the question is, what would the solution be? Alright? That would be an example of solving the numerical equation or numerical system. Now, the simplest methods to solving a system, how do you approach numerical problems? If you have the simplest method to approaching one, you always start with the human being, alright? The human being is gifted to solve things. And then you can use the computer as assistance. And the normal way we solve a problem is visually. We normally look at a simple graph. And the graph gives us a quick picture of the relationship. And where the graphs cross, the line represents the solution to each equation or each relationship. And so where the 2 lines cross is where both relationships hold. Right? So we call that the solution. Now a graph can't give you a precise answer, but a graph can give you a general answer or give you a region in which you expect your answer to be. And then you can turn to computational numerical tools to increase your precision or the speed at which you get to your answer. Alright, then there's this other method called Cramer's rule. I'm going to explain what that is. That's A. I'm not sure what A is as yet, so I'll get to that. So Cramer's rule involves a matrix. We'll talk about matrices. You all should know what matrices are already, but we'll discuss it a little bit more. And then we have another method which becomes a little bit more technical. That's mathematical substitution. That means actually going through, and you have your x and you divide by this and you move it over the equal side and do all those things, and substitution and all those things. That's what you all learned. You should have learned in at least CXC time, how to solve an algebraic equation. If you have 2 equations, you take one and you plug it into the other and you solve it, right? Those can work usually when you have about 2 or 3 unknowns in your system. But when you start passing 2 or 3, it starts becoming a little overwhelming. And so then we turn to some computational strategies. Alright, so these are impractical for larger systems or systems, especially more than 3 quantities or 3 variables. Alright. Now, the basis of many larger systems that we call Gaussian elimination. I think many of you may have learned it already, and if you haven't learned it, I'll give you a brief introduction to it. But the goal of the class is not for you to do the exercise of Gaussian elimination. That's, to me, a waste of your time. But it is for you to appreciate its application and to act. And the Gaussian elimination itself is just a framework, basic framework, but most computer systems really don't use Gaussian elimination. It was just a starting point in doing numerical computational analysis. Alright, it's a starting point. So if you appreciate the starting point, then you can appreciate now all the different variations to it, and your computational systems, such as, I hope everybody download Octave already. No? Octave. No, not add MATLAB. It's the same thing. So if you have MATLAB, you don't need Octave. But yeah, so what you'll learn is that Octave has already, or MATLAB has already packaged linear equation functions in it. Alright? It already has packages to solve linear equations. So we're going to really see what MATLAB is doing. Why should you be doing it when the computer can do it? The point is you should know what the computer is doing. That's all. And that's saying, so you should know what the computer is doing. You don't just, because if you don't know what the computer is doing, you really don't know what you should give to the computer. And then you have no basis of trusting what the computer gives back to you, because you don't know what the computer is doing. You just trust it so much, you can't do that. So you must understand what the computer is doing. So you need to understand the framework of these solution strategies. Alright? So what is a linear system when a computer looks at it? A computer doesn't see equations. What computers see are computers see little storage, little spaces of storage or elements of storage. It's like little boxes. That's all a computer has. All these boxes with information in them, and the basic data of a computer is something called the byte, which is in these boxes are zeros or one. Or when I say 0 or 1, it's just something or nothing. You put something in it, or you put nothing in it, and all that becomes interpreted as information. Alright? And a number is just a set of somethings and nothings. We use the binary tool system. That's what computers are based on up to now. And there's some new type of computing coming in called the quantum processors. Yeah, quantum processors that now come up with some other different thing that is very scary. And it's not just yes or no, it's maybe. Yeah, this maybe world now. Eh? Yeah, but anyway, don't worry about that. We're not there yet completely. Alright, so that is how the computer looks at information. It's just these blocks of, you could say, a shelf of information, and you have little pockets in there. So when it wants to express an equation, it just has these 3 blocks of information, or 2 blocks of information. It's a linear system. What you have is a matrix. Call it a matrix. It's just like a table or a shelf. And that's really how it is stored in the computer. So let us look at what really those blocks are. So this is what the blocks really look like. So this is our actual linear equation. This is our actual engineering statement, where the x's are the quantities and everything else is a constant. So here we have several equations. How many equations? N equations, okay, or N relationships. And in these N relationships you have In this case, n quantities that can change, or we call them, yeah, quantities that change, properties. Alright? In this case, it's the same. But some linear systems, it doesn't have to be the same. It can be different. You may have learned in engineering, number of equations must be the same as number of unknowns. Have you heard that say? Number of equations, number of unknowns, yeah. That's just some basic statement to saying something is solvable. But it's not absolutely true, so we're going to look at the variations to that. So you can have 3 equations and 2 unknowns, which can be solvable provided that you prove that one of those 3 equations is actually the first 2 combined. So it becomes 3 equations and 2 unknowns. But what I'm saying is, you may be presented with a system and you have 3 equations, but it's 2 unknowns. So these are the complexities that arise in engineering, and you need to know how to handle these different complexities. So we're going to deal with that. Alright? Now, what you'll notice here is a computer doesn't understand an equation. So what you do, you're going to try and express this linear system as 2 blocks of data. The 2 blocks are all these what's called coefficients. Those are some constants. And this is called the coefficient matrix. Alright? And then you have to the right the side of the equal side that doesn't have any variable in it. We call that the non-homogeneous vector. It's always a vector. Okay? It's also a constant. It's a constant, it's a vector. Now a vector is always a row or a column. Note, a vector is always a row or a column. And a matrix must be at least 2 rows and 2 columns. Must be at least 2 rows and 2 columns. Well, yeah, you can have a 1 row matrix which is a vector. That's what I'm trying to say. Alright?
You would consider the coefficient matrix a vector, the coefficient.
You would just say, you would call it a matrix, right? Okay. And there's another matrix now, which sometimes you can give to the computer. It's called the augmented matrix. What is the augmented matrix? It's just a matrix that combines together. Alright? So instead of writing out your equation, because you can write plus and equal side and those things, you just have the shell and you put in the constants. That's all you have, the constants. You are the one who understands it. The computer don't understand it. Alright? You know that this means this x1 plus that x2 and so on plus this xm. There are m variables here. Okay? But there are n equations. 1, 2, 3, n. So this is a case where you have different numbers of equations. Alright? This is the augmented matrix. So this is a way you can express a system to a computer. It's just a set of constants. But it's actually, in your mind, you know it's some equations, or linear equations. Alright? Now what Gaussian elimination does is the exact same thing you would have done if you were doing algebra. In algebra, you can add equations and subtract equations and so forth. Everybody know those strategies? You can add equations, subtract equations. It's the same thing as I say you can add and subtract rows. So all the computer does is just take a row, add it to another row, subtract another row, and keeps doing it until some rows go to 0. And eventually, you'll see, you change it to a form that says 1, 0, 0, 0, 0, 0, 0, 0, and something will be here. 1 times x1 plus nothing else equals that. So we found a solution and it goes on. That's the procedure. I'm not going to ask you to exercise that procedure. It's just explaining what the computer does. Alright? So what we're saying is the computer just does operations on rows, and it's just like when one does algebra. Alright? Again, you understand that the computer is your slave. That's how it should be. Alright? And the process is called Gaussian elimination. The goal is to eliminate every element in the coefficient part. For every row, you eliminate every element and make them 0 except 1. And that is the solution. That's why it's called Gaussian elimination. It's the process of eliminating elements till you get only 1, which must be the solution. So here's an example. So an example. So this is a mathematical system. You'll have to learn to do it for an engineering system. Some little rules of engineering. First of all, why this is not an engineering problem? First rule, in the engineering world, everything is a physical thing. This is a number. No number exists in the world. Number exists with something. And that's what I just said. Numbers exist for something. Numbers don't exist in the real physical world. So in engineering, everything must be associated with something. So like as a teacher, I drive home, what is your unit? Your unit is what thing are you talking about? And so it's a practice that an engineer has to start developing habitually, is that you always associate a number with units, with something that you're speaking of. Whatever it is. It could be dog, it could be anything. Alright? Now this matrix this would be what's called the augmented matrix. This is what the computer you give to the computer. Alright? And all it does is takes the coefficients. This is exactly the same thing to the computer as this is to you. Alright, now the other issue about the computer is purely a mathematical thing. It don't know what a dog is. So you have to now interpret what comes out, because it doesn't understand the physical world. It's just working with, as it says, zeros and ones. Sorry. Commander. Yeah. Right? You're heading on, alright? You're leaving out now. Even the kipper. Alright. I'll leave it with Clyde. Simpson. Sean, Lanier, Pusai, who never smile. Just ask somebody to fly first. Alright, so everybody see the augmented matrix? Alright, so here we go. Now I'm not going to go through all of this. It's just a little exercise. So you see. So first thing, they swap, they shift, they swap the roles, but that don't change the system, not true?
No.
Saying this is first or that second. So this is equivalent to that. Because there is nothing first or second or third about something. You just put in whatever way you want to put it. So in the the computer may have a preferred way to solve it. Okay? And just going. So we're swapping the equations. Now we're going to do some additions and subtractions and so forth. Now remember what an equation means. It means whatever is here is the same thing as what is here. That's what an equation means. It looks different to you, but it's exactly the same thing. So if I add 13 to this, right? If I add 13 over here, it's the same thing. But I don't have to put this 13, I can put this 13, because this is also 13. Alright? So when you add, so what we did is just added the rows. So whatever this is, well in this case we're going to add 2 times row 1 to row 2. That means I'm going to take 8 and add to this row. 2 times row 1, right?
Yes, sir.
Yes, 2 times row 1. I'm going to add. Oh, I'm here. So let's swap it. Try. Let's work with me. So we're going to swap it. So this is now row 1. Pardon me. I want to still have you look at the equation and not at the matrix. So here we're going to say we're going to add 2 row 1s to row 2. Okay? This is now row 2. Okay? And we're going to call that row 1. Alright? So 2 of these is really 26. So I'm going to add 26 to 4, that's 30, right? And I'm going to call that row. So I call that row 2. See?
Row 2 plus 2 row 1. So you're increasing row 2 by 2 row 1.
Row 2 plus 2 row 1
You
give you 30. So row 2 row 1s, it's 230. This is also 230, but I'm not going to put 2. I'm not going to put 26 and add 26 to this. I'm going to add this times 2. It's the same 26 because we say equal. That means whatever is over here is over here. And that's just a principle that the Gaussian elimination or the linear system computational methods use. It's just saying when you add rows, you are not changing your system. Alright? Not changing your system. If I say, not necessarily true, but if I say a family is 2 parents, mixed up, I'm bad children. Alright, so a family is 2 parents and 5 children. And we say that they define it as that. Whatever I do to one, I can do to the other. So I can say 2 families is 4 parents and 10 children. Suppose I say, so a family and a dog, or 2 families and a dog, is 4 parents, 10 children and a dog. Right? Didn't change anything. The whole thing is still holding together. Okay? Alright. So hold on. I realize. So we could go through a lot of stages. Lots of stages. I'm not going to go into the details of all those stages. And eventually you end up with this set over here. So this expression to the right here. And what this just means is 1 times x1. Well, this means x3 is 2. So we find the answer. This means x2 plus x3, which we are told is 2. And we just say x3 is 2, right? 6. So x3 and so now this coming to here is called Gaussian elimination. Just to this part. The next part is called back substitution. We're now able to take the simplest answer and then you're going to filter the answers back up. It's called back substitution. It's still a sort of elimination process. So back substitution now, you solve it and finish it off. Alright? So that's the general procedure. Note, whenever you ask the computer to solve a linear system, that's what it goes through. You don't have to go through, but you should understand that's what it goes through. I hope the other persons not with me have their Octave or MATLAB installed.
Yeah.
You all have MATLAB on your computers, I hope, or Octaves. And if you don't, just share with somebody beside you, please.
Yeah, sir. Any system of variables can use this approach to solve it.
Any linear system.
Yes.
So this is now now you see some things here. This is now what you would have never learned before in math. So you may have learned Gaussian elimination in undergrad, a way to solve linear systems. So that's a basic thing. But that's this ideal world. The real world, it don't go like so. There are all these issues that come up in the real world. And that's what we have to know as engineers grapple with. So instead of asking you to learn how to do Gaussian elimination, I need you to understand if it's really applicable, when it is applicable, what are the issues you have to address if you're going to apply it to a certain situation. Alright, it's not every linear system that it necessarily solves. Alright? So, first thing, if you have a linear system, that just means several linear equations. The question is, can it be solved? There are several possibilities of solutions. We have 4 different types of solution possibilities. Note them. First type is called a unique solution. Unique solution. What is a unique solution? It's one in which we know we have one answer for each variable, and we are sure of it. Well, we have one answer for each variable. I'm not going to say we are sure of it as yet, but the point is one answer for each variable. Now, sometimes your answer may be what's called well-conditioned or ill-conditioned. What does that mean? In the engineering world, or in the real world, I shouldn't say engineering world, in the physical world, everything has error. So your constants, that's the A and the B, those are constants. The constants have an uncertainty in it. For example, G, gravitational constant, 9.807 we say. But it's not really 9.807, you know. It just depends on where on Earth you are. One place on Earth is this, another place on Earth is that, so they average it and say call it 9.807. So there is a confidence for those systems. Engineering normally goes with a confidence of 0.1%. That's the confidence that we call an engineering confidence. That means when you go to an engineering table, it will be 4 significant digits usually. That means anything more than that is too accurate. Its accuracy is misrepresentative. So if I say, so I can say gravity is 9.807, but if I go somewhere, exactly the gravity might be 9.80659, right? Now if I say gravity is 9.80659, that's a lie, because I may go somewhere else and it's not that value. So what you do is you round it to the significant digits that you can say with some assurance wherever you are, it's still going to be that value. Understand what I'm saying? So because there is a certain level of precision in the real world or imprecision in the real world, that means that your systems that you solve will have a little variation in the possibility for your answers. So your constants A and B and so forth, they may be a little, they can change based on how precise your system is. That makes sense? Alright, good. So, a well-conditioned problem is one in which if you slightly change the constants, A's and B's, your answer changes just as slightly. But an ill-conditioned problem is where if you slightly change your answers, your solution changes significantly. Alright? I'm going to show you some examples of that. But in both cases, you get answers. Now, the computer don't understand what is ill-conditioned. It just gives you an answer, and it says that's the answer. Just like your calculator, you plug in a value, and it gives you to whatever significant digits that the computer screen can hold, or the calculator screen can hold. But that is a mathematical answer, that's not an engineering answer. Engineering answer has to consider how precise is it for the real world. So when you give an answer with all 10 digits, you're actually being incorrect, because you can't say it's that confident. The information you put in wasn't to 10 digits. So how can your answer be to 10 digits? And that's what I'm saying? But the computer didn't know that you didn't type 1.000000000. That means you're confident of all those zeros. You just type 1. That means you're only confident. That's what I'm saying. 1.5. What does 1.5 mean? 1.5 means anywhere from 1.45 to 1.55. That's what 1.5 means in engineering. Am I clear? That's what 1.5 means in engineering. But when you type in a computer, 1.5 means 1.5000000000. And if it's an 8-bit, it's 8 zeros. If it's a 16-bit, it's 15 zeros. Understand? So it works with, so the computer doesn't appreciate. So you need to be able to look at your problem and know if something is well conditioned or ill-conditioned. So we'll go into how you do that. Next one. Sometimes your system has no solution. But guess what? When you have a set of equations, how do you know you can solve it? There are ways to determine whether or not you can solve it. Because what you don't want to do is you don't want to be using your computer, plug in something. You know what computers do? They just keep trying to solve it. And they call it crash. Because the computer is in this perpetual cycle trying to get to an answer and never get to the answer. And computer crash. That's what they call it. Okay? So that's a no solution case in which you didn't look at your system properly and you think there should be a solution and there's no solution. You have another situation where you have infinite solutions or multiple solutions. It's a linear system. Usually linear systems only have infinite solutions or one solution. When it has infinite solutions, again, you get a solution. You think it's the right answer, but you have an infinite number of solutions. So you plug in something and you say you get the solution. That's not the solution. Do you know what Z means? Z means one, only one. It's not the solution. It can be a region, and you have something called the trivial solution. Trivial solution is for a certain type of equation where B. What is B? Anybody remember what B is? From the vector, the part on the equal sign, where all the B's are 0. When all the B's are 0, it's still possible that you can get a solution. You can have a simple equation or a simple set of equations where all the B's are 0, but there is a trivial answer to that. And the answer to that is all the X's are 0. we call that the trivial solution. And the implication of the trivial solution is that you don't want to ask the computer to solve and it gives you x equals 0 and you say, oh, we get the answer. Because that's called a trivial solution. Of course, that's the case. But there may be another solution. Okay? Now when you have a trivial system, the solution is what we call eigenvalue or eigenvectors. We can deal with that also. So again, I hope you're appreciating what we're doing here. We're not teaching you how to do Gaussian elimination. We're teaching you how to apply it properly, or apply how to approach solving a linear problem in a right approach, because not everything can be solved. So some of them may not be properly modeled. You may not have been looking at the system in the proper way, and so forth. So we have to consider all these possibilities. Alright? So here's a picture showing the different examples. This is what we call a unique solution. This is what we call no solution. These are two equations, right? No solution. Now it's obvious if you plot it, it's obvious. Maybe obvious, that is. Infinite solutions. This may be obvious. Like, why would you have two equations that are on each other and ask to solve it? In a normal linear system, it's not two equations. Maybe give me three equations. And the three are different. If it's two equations, the infinite solution means two equations are the same equation. So you can have a three equation system. And the three equations are three different equations. But essentially, if you do a substitution of one into the other, what is left is two equal equations. Okay? But 3 is just a simple case. But if it's 10 or 20, you can still have a case where you have infinite number solution. You can't just see it like that. So they have to be tested to identify the other. Okay? And this is the trivial solution. So these are two different equations. Everybody see that, right? And remember, as you learned when we just started algebra, y equal mx plus b or c, that b is that constant, right? And if that b is 0, we know that it goes through the intercept, right? It's the same.
Yes, sir. You know when it becomes an infinite number.
So there are approaches, man. We're going to go through other approaches.
I suppose you have three equations, like following it up to 1 point. Let's say, for example, up to 1 billion, and then the next paper.
No, you say what he just said is right. It's not a linear system. There's a different set of problems. We'll deal with that next week. Non-linear problems. So in the linear system, always straight lines. All right. So to determine if your system is solvable, you have to learn to determine two properties of your function. They're called the rank, and the other one is the determinant. The rank and the determinant. So I'm going to open MATLAB, or Active in my case. You guys can open it too. Alright, so guys, the screen thing now go work with Active, so you don't have to go open Active or MATLAB, alright? That is folks over at online. have octave. I'm going to go back to the same original problem that we had before. That one. I'm going to write the coefficient matrix. I want you to make note of it. You tell me what it is, alright? Actually, I can see it without. Hold on. Yeah. I can see it, it's alright. So, what we have is A. I'm going to make a vector called A. That's equal to. Alright, MATLAB rules. Everybody has done your, well, many of you, not all of you, have done your assignment. Your assignment just to get you warmed up in MATLAB.
Not graded, sir. Not graded. No, still doing it. I was taking it graded. I didn't submit it.
Yeah, no. No man, don't do, it's a practice. So some people have MATLAB experience. Some of you have MATLAB experience but not in what we want it, obviously. So. Anyway, so here's the deal. MATLAB. Simple way to do MATLAB. Whenever you're defining a vector matrix, you use a square bracket. Alright? Every element is separated by a comma or space. So, -2, 1, -1, 4. That's a vector. It's a row. If I wanted that to be A, I just close it and say that's a row. If I want it to be a column, every new row is separated by a semicolon. And it will be a column. So if I want several rows, I just separate the rows by a semicolon. Alright? I could just put a semicolon here and I continue. It just means go to a new row. 1, 2, 3, 13. If I make the error of not putting something, 3, 0, 1. Let's see what it does. So you can have a matrix. Matrix, you can have 3 elements, 4 elements in most of the rows and have 3 elements in one. That's a problem. Alright? So, up arrow to pull it up back. Let's put the last, there was a 0 right here, right? 301 minus 1. There we go. That's the, actually that's the augmented matrix. That's not the coefficient matrix. Coefficient matrix is just the first 3. This is the keys, right? You need me to zoom in more, or you can see it good enough. Zoom in. I'm going to zoom in. Alright, I will zoom in big time now. Better? Now I'm going to zoom in no more than that, alright? Alright, so now let me, since I've made a mistake here and put the augmented rather than the coefficient matrix, let me do something. This is what is called an assignment, okay? It's assignment meaning I'm going to make a little box we call A, it's a storage system, and I'm going to put this in it called an assignment. Right? No assignment
For the program.
Variable is like x, y, x1, x2, x3, those are variables in engineering, but I'm saying in computing, call it an assignment. Alright, so what I want to do is I want to redefine A as just these three columns. That's what it should be, right? So what I'll do, I'll say A equals, there's a little rule here. Note how we do it. A, that means I'm going to, whatever you do over here, after you do it, you're going to put it in a box called A. Right now, any A on this side of the equation is going to look in storage for something called A and do whatever it is with that. Whatever it does with that A is going to now store it in a box called A. So whatever it was before is going to be destroyed. It's going to now be different in that box called A. Now what we're going to do is, MATLAB does this. Curl brackets is for indices. Indices indicate rows and columns. Square brackets is for assignments. When you want to put something in there, you put the square bracket. But when you want to refer to something, you put the curl brackets. Alright? So I say I want to refer to what? The first three columns. But what rows are you referring to? All rows. So how do you say all rows? It's just using regular, you use that. Dot, dot, dot. This represents what we call dot, dot, dot. That means everything, you always refer to rows before columns. So I'm saying I want you to give me all rows, but columns 1, 2, 3. Dot, dot, dot. All rows is column. I think that's the way it's done. Cool. So this means that, you know, that means everything between. Alright. So I just destroyed my first A. Let me go back and call that first thing B. No, let me call it C. So we're calling that C. So now we have A, and we have, I'm calling it C, right? Now I want this to be called B, right? So how we, now these little things are just some very essential tricks. Very, very essential tricks. Because people, when they do programming, you'll be amazed at how many unnecessary how much unnecessary steps and typing, and when, yeah. You want to, no, press up, just press up. Press up scrolls through all your commands. No, I press up to A, up to the previous, and then I back space to A. I press the back around and change it. I just did this. I just went up to this. Then I went across and type C. That's all. Yeah, just go up. So now I want to just refer to the last column. Simple. You just say all rows last. That's the actual word, last. So it's a B equal what of C? Remember, these are the reference or the indices. All rows but the last column. Remember, whatever is after the equal refers to the column. Last or end. End. Use end. Take his end. Okay? I'm calling this C. So I'm saying I want you to take all the rows and only the last column of C and call it B.
Is there another way of taking the first column of C?
First? No, there is no first because 1 is first. But we say end because sometimes you don't know the end. You know that the first is always 1, but you don't always know what number the end is. You understand?
You couldn't put 4.
Huh?
You put 4 into that end, we get the same.
Yeah, man. That's because you know it is 4.
Okay.
What I'm saying is, in the engineering system, you may be in a situation where you don't know how large the system is, and you want to take off the last. You just say end. Right? But you can have a scenario where you want to know the first, but you don't know what number the first is. Number of the first is always 1. So there isn't a special number for the first, or a special variable for the first. Alright? Note, there were some important things. I cannot be used as a variable or a storage. I is numbers in math engineering, I over I. I is the imaginary number. Stored. Alright? Other things. Pi. Next one. E. There are a set of them. I'm just giving you a few examples. Okay? Just a few examples. Those are common, very common for engineering. You about them. E is a special number.
Special number 2.1.
Yeah, it's a special number. It is the exponential decay number
Okay.
or exponential rise number. It is. Yeah. Exponential decay or exponential rise number.
So kind of is it that Octave has now stored what you call
Yes. So if I just type B without nothing, okay, you're asking it to tell you what B is.
Okay.
Alright? But I'm just letting you know that there are some variables that you should not toy with. Alright? J, let's see if you type a variable that you didn't do anything. J is 1. J is the same as I. Alright? K, you're like, what is K? We don't know what K is. So that's it. Okay? Alright, every variable is stored. In Octave, they actually have, it is MATLAB too, you have this place where it tells you everything that you've been doing and all this. So you have stored A, C, ANS, ANS is a variable. So if you don't give an assignment, like this is not an assignment, this is just an operation, but you didn't tell it to save it to something, it saves it to a variable called answer, ANS. ANS. So before ANS was this, and then I type this ANS is now that, and I type that. So if I'm looking over here, this is the table that shows what the values are. You're going to see ANS keep changing. The ANS was first, this value, then ANS changed to that, then ANS changed to that. Okay, it can't be seen because I can't zoom in on this. But if you double click on, see if I double click, if I can open it. Okay, copy value. What did I just do? I went over here, I right clicked on C, and I said copy value, and I just said paste. So it copied C, and there it is. It's the same thing that I typed out for C. Okay, but I got it by copying, told it to copy what is saved here. And I just said paste, Control V, and this is what came up. Note, if I press the equal sign now, it's going to assign this to a variable called ANS, because I can put an assignment. So what's the assignment? Control V is to paste. No man, the copy I write here, I just say copy now. or copy value, sorry. Right click on the name, on the name, and you'll see a little menu, drop down menu come up, and you should see copy value. There's it. It's not abusing. Alright, so and if I press equal here, you realize I didn't put I didn't do an assignment. What's an assignment? I didn't say this is equal to something. So it's going to store it. If you don't do an assignment and ask it to do an operation, so you store it to a variable called ANS. Whatever ANS is, it's going to throw it out and put that for ANS. Alright? So now ANS does change to that. Alright, so now I need to show you something. The first and easiest way to do a solution in MATLAB, let's make sure A and B are correct. A and B. Good. Now recall, A is a vector. I'm sorry, A is a matrix, but it's just a coefficients, right? And B is a vector. I can write it this way. I'm going to open a little spreadsheet. Let me go back to this. Everybody saw this. I'm going to open an equation editor. You can see it. Hopefully everybody can see what I'm about to type. Alright, now A is going to be, how do I do this again? -2, LibreOffice. Come on, it's Windows. Alright, remind me of the variables. Minus 2, 1, minus 1, what else? Alright, that's us A, right? And B, I mean the next row for A. 1, 2, 1, 2, 3. 1, 2, 3. Hold on, let me scroll up so you can. Next row. 3, 0, and 1. Alright, so that's A, right? That's A. Should I do it that way? That means determinant. Note there's some nomenclature things whenever straight like that, this means a determinant. Alright, just so you know. We'll talk about what that means soon enough. Whenever these lines are straight, it means determinant of this matrix. So I'm changing it to a square bracket. So a square bracket just means the matrix. Alright? Alright, so that's A. What is B? B is 430 negative 1. 413 and negative 1. That's your B, right? Now we're going to do a multiplication, it's a matrix multiplication. This is how it normally would be done. Please note. We're going to type what X is. X is actually X1 and X2 and X3. I'm working out these kinks, but this is why I'm trying to set up the tablet so the people online can see what I'm about to do, but they can't see it right now. Alright, so A11, A12, A13, A21, A31, A22, this is A. I'm going to use the matrix to write the equation. I'm going to multiply it by x1, x2, x3. This is how you multiply matrices or vectors. The same thing as the dot product. Whatever the dot product, first element times first element, or second element times second element. So I'm putting it like this. I'm multiplying these two things. And the answer is like 2. It's like we want to know what's here. It's this and that. What's here is the dot product of this with that. That's what I'm saying. What's here is the dot product of this with that. And so on. So let's look at it. And what we'll see, B1, B2, B3. Let's do it. X1, dot product means first times first. So it would be A11 X1 plus A12 X2 So that's the first row. This is now one element. This was 3 elements. Okay, see that? This is one element, another element, another element. When I multiply, all of this is now one element. Okay? Note, this is the equation. What is this equation? That was the original equation we started. So we call this A. We call this X. I'll just say X. B. So A times X equal B. Alright, and just like in algebra, and with the vector, usually you put, depends on the type of math system you're working with. So like they put two hats over that means the matrix, and they put one as a vector as well. Alright, now in algebra, it said, if you said AX equal B, and they said sub, I'm not saying you're a vector and a matrix, these are just scalars. And they said solve for X, what's the answer?
B over A.
X equal?
B over A.
B over A. Good. Now, if it's a vector system, it's not so simple. I'm going to show you. So let's go back to the. So in the vector system, A is a matrix, X equal B. Now note, I have to try and get rid of the A. How do you divide by a matrix? What you really did was you divide both sides by A. Is that what you said you did? So how do you divide this? That's the question. You have this matrix, which was A11, A22, and so forth. That was the matrix. How do you actually do a divide? That's a tricky problem. The way you do a divide is you actually have to multiply it by its inverse. Okay? That's what you did over here. You multiply the inverse, 1 over A. But for a matrix, inverse of a matrix is not 1 over those things. It's called the inverse of the matrix. And you have to say where you multiply it. So you have to actually say inverse of A times A. You realize I have to keep it before it, right? Because if I put the inverse over here, you have a problem. I'm actually saying the X is multiplying by the inverse, which actually cannot work because the inverse is going to be, the X is like this, X1, X2, X3, and the inverse is going to be the inverse, some can't explain what it will be. You can't really say what the answer will be. So it's confusing. Alright? That makes sense. The rule is this, I can't do a dot product. Why I can't do a dot product? Remember? First times the first, second times there is no second, third times there is no third. Realize there is no third? Remember, it's first of the column times the first of this row plus the second of this column times the second of there is no second in this row. So we can't have X be multiplied by the inverse. Alright? So what we do is we have to put it the other way and multiply this by the inverse. But it's still rules of algebra. So whatever I did here, since this is equal to this, I must do exactly the same thing. Exactly the same thing is put the A inverse on the left side of the B and then multiply by B, which can work because A inverse is going to be a 3 by 3 and this is going to be B, which is a 3. So you have 3 elements column, 3 elements row, so you have an answer here. And that's what I just said. So that will work over here. So whenever you multiply a vector by its whenever you multiply a number by its inverse, what's the answer? 1. Good. When you multiply a matrix by its inverse, the number is also 1. By the way, vectors don't have inverses. They have to be square matrices. Alright? So this time this is 1. But 1 for a vector is called the identity matrix. It means one other matrix. That's all it means. One other matrix is, in this case, it's going to be 1, 1, 1, 0, 0, 0, 0, 0, 0 times x, 1, x2, x3. This is the identity. So this becomes the identity matrix times x. Identity matrix times x becomes x. Remember, identity is like number 1. 1 times anything gives you back the same thing. So if you look at it, x1 times 1 is x1 plus 0 plus 0. So the first is going to be x1. Then next row, x1 times this is 0, x2 times this is x2, x3 times that is 0. So the next one is x2, and the last one will be x3. So we see that x1, 2, 3 times the identity gives you back x1, 2, 3, because the identity is like number 1. Alright? Like number 1. You might be wondering why I'm going to have this. Don't worry. The point is this: when I multiply this times this, I end up with x. Remember, that's what we're solving for, x.
When you get the answer right
on the other side is the answer. So the answer is whatever is A inverse times B. That's the answer. So we're going to do it in MATLAB now. Or Octave. Where's my Octave? There it is. So here's my Octave. So x is equal to, it's called INV, that's inverse of A times, by the way, MATLAB means matrix lab. So it understands all the rules of matrices. So if you put the thing in the wrong order, you're going to say you have a problem. Anyway, inverse A times B. That's what I said x should be. So that's the answer. That's it. But guess what? If you don't understand linear systems, something that simple would make much sense to you. There is even a simpler way of writing it now. Note, I am here. Okay? And I want to get rid of A. Instead of writing A inverse, there's another trick we use, which is we imagine dividing by A, but we divide on this side. See, I type this, I write the divide, because it's to that side. Okay? Right, divide like that. I want you to note that. I say, I am dividing by A to the left. We call it under. Just like when you say 6 over 2 equals 3, I could also say 2 under 6 equals 3. Okay? So it's like saying 2 under 6. When you put it in that form. So this is called the under operation. This one is called the over operation. So let's write it out. Just to prove it to you. So I can say 2 under 6 is 3. Same as 6 under 2 over 2 is 3. Understand? So I could say A under. Now what is A under A? A underneath A is the identity matrix. Right? So all of this will become just X. So I'm going to say A under B. X equals A under B. Same exact thing. Alright, so I just say A under B. Got it? A under B. I just said inverse A times B. The same thing as saying A under B. Note, you realize this gives no decimal points, and this gives some decimal points. So what that is saying is that how MATLAB approached the two are two different methods. The first one was approached by reordering inverse. Doing the inverse of something, they actually just shifted some things around until they get to the answer. But to do the under was actually, they went through a set of significant computations. And whenever you do multiple computations, errors come up. So that's why you have 0.000. It's not exactly one they got. Because the way they approached it is different from the way they approach getting to this answer is different from the way they approach getting to this.
So you're saying that you would have like 10 more decimal points to probably
You get some difference in the answer. Note also, their speed also of computation depends on the type of system. Now all of these don't matter to you, but you see when you're starting your assignments, your projects, you're going to have complex systems which you'll model. And a typical complex system may have 1,000, easily 1,000,000 points. You don't actually type in 1,000,000, you know. You let the code come up with 1,000,000. You just put in some for loops and it just spit out all the numbers, and it's, yeah. So it come up with 1,000,000 points. And then it has to solve it. Yes.
like 2 under 6 versus the 6 over 2, same thing, right?
Yeah.
The scalars, but for the matrix, it's right, A under B versus B over 2. Wouldn't read it as that.
Didn't read it as the same. Because these are scalars, these are not matrices, really exactly the same thing. But this one is 2 operations I did. I actually asked it to do 2 operations. The first one is I asked it to find the inverse of A. Here I didn't ask it to find the inverse of A. I asked it to do 1 operation. Okay? And I can't tell you how MATLAB approaches, but how it approaches is not the same. That's how it approaches that one. That's why it's 2 different answers. No. I was making a point that what was the point I was making? Alright. So yeah, we can have, so when I was doing my studies, I had to solve this I was a chemical engineer problem. So I was doing some computational, some chemical reaction something, right? And I had to model a system. It was about 10 different parameters, nothing too significant. Or 15, 20, about 15, 20. Linear system though. It was linear in a differential equation. It wasn't linear, just plain linear. And speed matters now, because how would I do it? I'd log in, I'd set up this system, and I'd actually have to give it a set of problems to solve. And I set up a code, it was the same MATLAB, and I would log into the school, log into the system, and set the code to run, and then go back next week. That is when it finish run. Yeah, go back next week. If it don't run. No, when it's like that, you better select the best approach to get into the answer. Okay? Because for you it makes no difference now. So one may have taken 1 millisecond, the other one takes 10 milliseconds. For you it's nothing, because it don't make a difference. But 1 day and 10 days is a big difference. Alright? And when you're doing your physical systems, or let's say if you do a finite element problem, Normally the approach is you break up your system into 100 parts or you mesh it out. And then you're actually making a large matrix. When you make that large matrix, you better pick the approach to solving that system that gets you to the answer more quickly. Alright? But you should see that all these ways of getting to the answer, they are essentially the same, but if you can appreciate what each one is, if you can appreciate what each one is, you are able to pick the best way to get to your answer. Alright, so the next thing about this is rank. So I had defined something called C, and I said there's something called rank. So let's say rank C. Rank C is 3. What does that mean? No, rank 3, even though you had 3 equations, remember I said sometimes you have more equations that are independent. That means I could have had 3 equations, but I could have put some together and realized it's really only 2. Remember we talked about that? Rank is the actual number of independent equations. So you may have 3 equations, but find that the third one, let me give you an example of 3 equations that are 2 independent. Everybody write 2x plus 3y equal 0. Write x minus y equal 4. 2x, what was the first one? 2x plus 3y equals 0. Just type it here. 2x plus 3y equals 0. What's the other one? X minus y equal 4. Add the 2 equations. 3x plus 2y equal 4. Aren't those 3 equations? But how did I get this one? So it's not 3 independent equations. These ones were independent, and that means I thought of this one and I thought of that one. Completely not related to this one. But this one is absolutely related to both of these. So now I'm going to plug these 3 equations into MATLAB and rank it. So
What's the definition of ranking again?
we're going to look at it now. Actually, I'm going to put one more. Let's put Z. That's so you're clear, because it makes you appreciate it a little bit more. I'll put a third one, and I'll put Z here. So it's going to be 2Z, right? Adding the 2 equations. Everybody agree? Alright, what is the augmented matrix going to be? It's going to be 2, 3, 1, 0. 1 minus 1, 1, 4. Let's write them out. So you tell me them. So A equal 2, 3, 1, 0. What's the next one? 1 minus 1, 1, 4. The last one is 3, 2, 2, 4. 3, 2, 2, 4. Huh? No, that's a C, right? Augmented matrix, sorry. We're talking about the augmented matrix. Ah, nice matrix, not true. So suppose you had 3 equations and you thought you could solve this, but it's actually 2 equations and 3 unknowns, because one of those equations came from the first 2. Understand what I'm saying? So sometimes you may have a complex system and you think you can solve it because you have the same number of equations unknown, but you don't realize that the rank is not the same thing as the size. So if I say rank C, I get 2. Okay? It actually did Gaussian elimination and saw if you got a row that said 0, 0, 0, 0, 0, 0, 0. That's all.
So that we infinite solution.
Right, so it's an infinite solution case. Or the problem isn't defined enough for you to solve it. That's what it means. Alright? The same 3, 5, 4 as this, but this one can't be solved. Alright, let's write.
Why can't it be solved again?
Because it's two unknowns. It's two equations and three unknowns. X, Y, and Z were the unknowns. But it's only two equations. We got the system from. I wrote three equations, but one wasn't independent of. But one of them was dependent on the other two. Remember when I said, when we started out, I said when we have an engineering system, what you have are these different laws. And you may say mechanics. You have some variables based on mechanics, and I may have a variable based on physical science or chemistry, and something on electricity. What we're saying, these are independent systems. But I can say, okay, I'm going to do a mass balance and then do a mole balance. It's not quite independent. They're related. You may end up with some conflict here. You have to be careful that when you're looking at a linear system, that the equations that you use to characterize it are truly independent of each other. But if you really want to know, you just test the rank. Because when you test the rank, you save yourself the hassle of trying to force the system to solve something that can't be solved. So when you test the rank, you say, oops, I have to go back to my model and find out what physical law or phenomena am I not modeling.
So to be clear, what answer from the wrong would tell you that they are.
Okay, so there's something called a rank, and the other one is just the rank is called the number of it's just the number of rows, a number of equations. So if the rank is less than the number of equations, the system, let's look at this is it.
There's a number of unknowns.
Here we go. R is called the rank. M is called number of unknowns. N is called number of equations. Right. The rank is less than the number of unknowns. Then we have infinite solution. If rank is equal to number of unknowns, that just means number of equations. Now, remember what you guys used to say, what I used to say? Number of equations equal number of unknowns, you can solve it. No. Number of independent equations equal number of unknowns, you can solve it. It's not number of equations, but number of independent equations. So how do you know if it's independent equations? You have to do the rank of the equations.
Answer, this only applies to linear equations.
Or the linear equations.
So once R is greater than or less than N, then you don't need to solve the solution.
So if R is greater than N, you over-constrain your system. You tell it to solve, it can't be solved. One of them, it can't be solved because you need to constrain it more. The other one, you actually messed up in the model. You did something impossible. That means there is no solution. You looked at the problem in the wrong way. And that's what this means. The rank is greater than the number of unknowns. Now, as I said, if your rank is equal to the number of unknowns, can you trust the answer? Not necessarily. That's what conditioning is, and that's what the issue of trivial solutions is. That's a different matter.
So the first test the rank.
First to test the rank. So at least the rank will eliminate infinite or no solution. Then now you have another situation, which is now you have a trivial, which means eigen solutions, which is trivial, or we will have ill-conditioned problem. That means it's still one solution, but it may not be appropriate. You can't trust the answer. Alright, so ill conditioning has to do with whenever you slightly insignificant change in the system means a significant change in the solution. I can't tell you what it is for other systems, but in chemical systems we call it testing the sensitivity. Term called sensitivity. When you have a lot of chemical reactions and they want to say test the sensitivity, it just says if I change one of the chemicals little bit, will it result in a very different set of output products. Call it sensitivity. Okay? So if your system is such that just a little change in something results in a lot of difference, then you can't, as an engineer or as an experimentalist, say this is the answer, because there was some error in the original information, and so you have to appreciate that there therefore is a very large uncertainty in the final answer. Alright? We call that ill conditioning. So if you have an ill conditioned system, we'll tell you how to test that soon. If you have an ill conditioned system, you have to look for another approach to solving your problem. So you realize this whole exercise is not teaching you how to do the linear solve the method of doing a linear equation solution. It is how to understand the validity and the likelihood of having an answer, the reliability, so you don't waste your time. That's pretty much what this is about, and how to lead you to the best approach to getting to your answer. Alright? So you have to look for another set of equations, for example, or you might need to find a third equation. It may be that you're not looking at the problem the right way. If you're ill conditioned, that's what all of those imply. Alright? So ill conditioning, you're going to use a property called the norm. The norm of the matrix. Again, this was something in MATLAB. You just type norm. Quite simple. I'm not sure if there's I think there may be a condition. Let's try. It's a norm of not the augmented matrix, but the coefficient matrix. So let's look at it. Norm A, that's a norm. And I also can say norm A inverse. Okay? Norm. There's also condition A. That. Now note, what the condition is really what we're talking about. This number, the condition of A. Condition is a number, if it goes beyond 10, you can get a little condition. If you reach 100, don't trust it. If you reach 1,000, completely untrustworthy. That's what this number is implying, the condition. Now you realize there are two numbers that used to get it. It's the norm of the coefficient times the inverse of the norm. So if I multiply these two, I get approximately that number. Now let's just check. It may not exactly be the same. Yeah, it is the same in this case. Anyway, so if you look back at the notes, the condition is this. This is called the norm. Okay? Double bars is norm. Remember I said the single bar is the determinant of the matrix. The double bars are the norm of the matrix. What does a norm really mean? What does a norm of a number mean? What does norm mean? Everybody know what norm means? Norm means size. It is like the magnitude of a vector. Something squared plus something squared plus something squared plus something squared. We call that the magnitude. It's like the norm. Let me explain how we get the norm. Just like if I write -2, let's write a number here and give it a variable x equal -2 -5 3. Yeah, 3 1. I'm gonna put -1. Alright, let's see if I can get the norm of this. The norm we can give it a check. Let's do a quick check, some little tricks. X squared. Now note, this means element by element operation. It means 2 squared, 5 squared, -5 squared, 3 squared. No, or x, if I didn't put that, it means a matrix operation. Where I said x squared without the dot, I'm saying do like dot product and I'll do something. Of course, if I said x squared, you tell me I can't do it because remember the number of columns is the number of rows. I can do x times the transpose of x squared. And everybody know what transpose means? Transpose means if one is a row, the other one is a column. Anyway, so the x times the transpose of x would give me, let's do this first. Everybody see that? I'm going to sum it now. I'm going to take the square root now. That was a norm, right? Everybody else said norm? So the norm, well, alright, so note about norm. The conventional norm is, it's called the 2 norm. That means square and square root. You take the square and then you get the square root. But you have norm for every. You have one norm, which is called the magnitude norm. That just means this plus the magnitude of that plus the magnitude of that plus the magnitude of that plus the magnitude of that. That's a 1 norm. Or this to the 1 times the root, which gives you back the same value. Understand? It's a magnitude. It's called the 1 norm. Then you have the 2 norm, you have the 3 norm, you have all the way to the infinity norm. By the way, the infinity norm is not going to be infinity. It's actually going to approach a number. Okay? So that's a norm. I could have done it this way. I could have said x times, let's see, x is a row, so I'll do a column now, x transpose. This is a transpose. That's a dot product I just wanted to do. First element, hope you understand. One x is going to be like this, the other one is going to be like that. So it's going to just give me one answer. It should still give me 40. Okay? Everybody see why that is so? Do I have to go through that? You see it? The x was the row, x transpose is a column, multiply two of them, first element, add to the second element, and so forth. That's how I get the 40. So that's the norm. The standard norm is the, let's do note. Now, what did I do here? The conventional norm is the 2 norm. But when I put this number, I tell which norm I want it to be. So if I leave it blank, it's understood to be 2. If I don't put that, it can be any number.
The 1 norm is 4.
What is this? 4 and 5 is?
4 and 10 is
Hold on. No, man. No, 2 and 5 is?
minus 3.
Oh, it's
No, the magnitude. We're doing the 1 norm.
Oh,
2 and 5 is? And 3 and 1 and 1.
Okay, so the next don't matter.
That's the 1 norm. If I do the 3 norm, the cube, right? The cube is going to be the magnitude of the cube. So it's going to be 2 cube. 5, not negative 5 cube, but 5 cube. Always work with the magnitude. 3 cube, 1 cube, 1 cube. And then take the cube root. So the best way to do the 3 norm, if you weren't letting the computer do it, it would be as simply as saying abs, you have to leave? Okay. Abs x. So put everything first in that, right? Then I'm going to put it to the cube root. So I'm doing the 3 norm. Abs means absolute value. Abs means absolute value. I'm going to do the cube root. So how do I do the cube root? Just put this. That's cube root, right? Then I'm going to add everything together. No. Not cube root. That's cube, but that shouldn't be the... Oh, sorry. I shouldn't have said x. Alright, let's go back. And call this y, okay? Good. And then I'm going to take the cube root of this, right? Of y. The cube of it. Sorry, not the cube root. Good? And I'm going to add everything together. It's saved here. I'm going to add everything. Sum. Let's go up to sum. Oh, it's answer is there already. Good. And then I take the cube root of that, right? Oh, so I just say to the power answer to the 1/3. So that's the norm 3. Understand? So if I just did norm 3, I'll get the same thing. And it goes all the way to infinity, you still get a value. Now note, it really don't matter which norm you take. Norm, you can go all the way to infinity. It's going to kind of fluctuate around a number. The number to fluctuate in this case is clearly somewhere 5 to 6. Norm 1 was, what was norm 1? 12? And then it dropped down to 6, and it's going to kind of fluctuate around 5 or 6, but it's going to stabilize as the number gets bigger and bigger until it gets to 5. Alright?
What was the need to have norm 3?
Alright. I just noted it because remember that the norm is a picture of the size of the matrix. If the inverse of the matrix is a very large number, okay, if you have a very large number, such that if you invert it, you get a very small number, then it's an imbalanced system. That's all we're saying. It's a very imbalanced system because part of your operation has to do with inverting things. So when you invert it, you get a much different number in terms of order of magnitude. There's not much trust in it. The norm, it doesn't matter what norm you take, but I just wanted you to see it because guess what? You may Our problem, you have to deal with the norm, and then you buck up that there are all these different type of norms, and you think, you start fret about it. So I'm just letting you know what norm means. Okay? And any norm would still give you a reasonable answer. Because all the norms are giving you a number 10 or less, in the region of 10 or less. All the norms from norm 1 to norm infinity. Remember I said you'll be approaching 5 as they get larger and larger? So it don't matter. So the most common norms are the norm 1, norm 2, and norm infinity. Those are normally the norms that are used in different scenarios. But the norm that is kind of a quick and easy one to do is usually norm 2. So norm 2 is normally accepted. But it depends on your scenario. Like when you want to say what's the length of a vector, you know it should be the square. It's a different type of norm. We call it the norm 2. It's the length of a vector. That's how we know it, right? The length of the hypotenuse. The x is one element and the y is the second element. The norm is the hypotenuse. Understand? The length. Alright. So ill conditioning, that's all you need to understand. Ill conditioning is just, you can just write condition. MATLAB does that. A long time ago that wouldn't have been done by MATLAB, but now it's done. So you don't even need to know what norm means, but you need to know the basis of things, so you don't just trust the computer. That's why I have to do this. Alright? Alright. I think I'll have to pause. No, I will explain this to you. Now, when you solve, so everybody should be clear. You need to know when a system is solvable. That's all about the rank versus the number of unknowns. That's what you use to determine if a system is solvable. If a system is solvable, you need to know if it's trustworthy. That's about the condition. Good. Now, so that's settled. Now you want to solve a system. If it's just one system you're solving, you can just use all those different ways. You have a general solution system. In MATLAB, you don't have to say Gaussian elimination. You just say A under B, and you give your answer. Or you say the inverse of A times B, it gives you an answer. Alright? That's a simple case. Sometimes you can have a system that you repeat over and over again. But the only thing you change is the B. It's a normal engineering problem. In engineering, you are solving a set of equations, and when you finish solving the set of equations, you need to repeat the procedure, but you need to change the set of equations. But sometimes the only thing that changes in the set of equations is B, the B terms. All the A's remain the same, but the B term changes. Alright? When you have a case like that, you have a procedure called LU decomposition or decomposition. What you do is you can halfway solve a problem and then do the second half. Now, whenever you repeat your problem, you don't have to repeat the first half. You just repeat the second half. That's the part with the B. So we call it LU decomposition. Let me show you a simple same A, different B. Now, let me hold on. LU. Alright, now I'll go into it. I'll go stop here.
What would have been the advantage of it? Why not
What?
just continue?
No, alright. The advantage of LU decomposition. Let's say it again. I have a problem. I'll ask you to read upon it a little. I have it here. I thought I had it here. Alright. So what you will be doing is you halfway, remember, just like in Gaussian elimination, you have a part of it which, for example, is elimination, and then you have the back substitution. It's broken down into two parts. You can have actually the 1A expression, and you break it up into two matrices, which we call L and U. L means the lower matrix and the upper matrix. Okay? The lower and the upper matrix. And then what you do is just solve just for something called Y. I have to find it for you. Alright, let me just put it over here. See if we can just pull it out of my head. So AX equal B. I'll change A to LU X equal B. And LY equal B. The point is this: you solve it part way, so it's normally a little more effort than solving one problem straight. So if you're solving one problem, it may take, let's say, 10 steps. When you use LU decomposition, it may take 6 steps and 6 steps. Okay, because you're doing this pause and so forth. Now, when I want to repeat the problem, all I do is I change the B. When I repeat the problem, I have to do the 10 steps again. But when I do LU decomposition, the first 6 steps don't change. So I just use the whole first 6 steps. It's already solved, and I just do 6 more steps. So it's when you have a sequence of linear systems that you have to solve, where all linear systems have the same B. Instead of resolving the whole system all the time, you decompose it into 2 problems that you halfway solve, and that halfway solution will work for all the problems. And the second half is all the part that you redo over and over again.
Oh, they save time.
Save time. Just do the first part. So if it was just one that you're solving, it takes more time.
Okay.
But if you're repeating over and over again, you won't repeat the full 12 steps. You'll only repeat half of the steps.
Okay.
Alright? That's called LU decomposition. And what we do is, again, Octave have that for you already. Here is A. I can say LUA. It just did a LU decomposition. Let me write this though. L U A. Alright. Next rule of MATLAB or Octave. When I put this, I mean please don't show me the answer. Just save the answer. That's what this is. This is saying the answer you're giving me is actually 2 answers. First answer, save it as something called L. The second answer, save it as something called U. That's how you do a double assignment. You can do triple assignment, any number of assignments. It all depends on the function. Okay? So if I look now, I have L, because I just told it to save something called L. That's what L is. and I told it to say something called U. That's what U is. Okay? So, let's type L times U. L times U. You might say, what is that? L times U is A. Look. What it is decompose A into a product, L and U. So before it was just A x equal B, now it's L times U times x equal B. And then so it's a
Scroll back for me. When you add L, comma U equal.
So what this is an assignment. I'm calling name it L and negative, but this is a function in MATLAB. MATLAB, you can tell it to do an LU decomposition. So I told MATLAB to do LU decomposition of A. And assign, you're going to get two variables. The first one, I want you to call it L. I could call it
B or Z.
B or Z.
So hold on. MATLAB decides how to do these variables. That's what
Yeah, so I'm letting you know that all these things are already there for you. But you need to know what it means. It don't make sense. You just use MATLAB when you have no clue. You don't just use functions, just use, you have to understand. So, another thing L to LU means this is called an upper triangular matrix. Note, everything above the diagonal and above, now below the diagonal is zeros. Upper triangle, it's like a triangle where it's only the top part of the triangle that has values. The bottom has nothing. While L is called the lower triangular matrix. Lower triangular matrix, right? In this case. Oh yes, lower triangular matrix, everything below the diagonal, but the diagonal is this way, is equal to 0. Alright? Right. So upper or lower, alright? Which is just a decomposition. Now you have other types of decomposition. Now a little help for MATLAB is this thing called help. Good. There you go. So you're going to know something? Let's type it. Tell you, read it, understand, you don't understand, just read it, make a little sense. You do something and you get an error, actually read the error. Something good about MATLAB is to really explain it. It's a teaching, even your errors are a teaching experience. Alright? Read the error will explain some of the rules of maths and engineering. You say, oh, I should have done that. Like if I say x times x. Remember we defined x already? X times x. Oh. So let's go through. Yeah, man. That's what you just read there. But just read, and there are other. So when you get to the end of this, you will see also. There are other types of decomposition that's possible. C also. Alright. QR decomposition, QZ. These are some other types. You can't take no more. So that's what the help does. Let me give you an example of an error. So if I say x times x, we know that those are two rows. Bad words. Up is 155. Alright, we'll stop here. Later. So x times a. Alright, thank you for your time. Remember, the goal is not to teach you how to solve simultaneous equations. The goal is to understand the validity, to appreciate why you do these things, when you don't do them, etc., etc. Alright? No man, the more you learn, how much you don't know.
Exactly. And that's, years now where they appreciate it first, man. When they start, uncertainty of knowledge. Yeah, we imaginary numbers, and start of a first explosion, a lot. So we want to go 20,
Thank you for your time. Alright, so, alright, this is a lot. So, something like this now, you may need to hear it again. So, it will be posted by Monday. A video of the whole session. Alright? And we still have to work out the kinks. I know that it seems Jayan drop asleep. Oh, she typed in her message now. She said, "No, sir, I'm not asleep." Anyway, it didn't work out so well in terms of you seeing everything I'm doing, but it's saved in terms of, because some of the things that were on my screen you're not seeing, and I'm not sure why. So we're working on that. All right, Jan. But the point is, I've saved the whole. I guess you all saw the first lecture, right? You saw the embedded video, right? So I'm going to do it for this lecture also. All right. All right, you're welcome, dear.